All right, I have two main things I want to do. Lecture 4 notes, which we haven't even talked about yet, talk a little bit about how transistors are made, but more importantly, how they're shaped, what their structure is, and I want to talk about a little bit about the trade-offs between in the design of the device. It's likely that none of you will ever do the design of a bipolar transistor. Maybe one or two of you will. But you need to understand how bipolar transistors work and what some of the trade-offs were. And eventually that's going to lead us to how things are modeled. And the homework is really about biasing and things. So you may have to read ahead and use some of the background to practice some of those things. So that'll get us finally to circuits, which is what we're mostly here for. All right, I asked last time what fraction of the class was taking the 5322, and most of you are. So most of you will be familiar from that with how different things are done, but in building semiconductor devices. But I'll go through it quickly here. So the first thing that gets repeated over and over and over is how we make patterns onto the semiconductor wafer, onto the semiconductor chip, and the process is photolithography. So just quickly, without spending any more time than I have to on this, we start with silicon. We grow a silicon dioxide layer, which is a story unto itself. Silicon dioxide is silicon with two oxygen atoms. In order to do that, oxygen or water atoms have to diffuse through the silicon to get down to the surface where they react, and things happen from there. We then coat this with photoresist. We don't need to know how or anything else about it. We then expose this through a mask which has an opening in some place, so it's opaque in some places and clear in others. Then we remove the mask, having exposed this to appropriate light, which sensitizes the photoresist chemicals. We can then remove either this part or this part. In the example I'll show, we're going to remove this part. We will then expose the silicon dioxide to whatever impurities we're interested in, or the surface. We may etch this away with a chemical. So that might be what happens is we etch this away. It would be hydrofluoric acid usually. And then in most cases we would remove the photoresist. There's plenty of variations on this. But now we've put the structure using a photolithographic process. We've created an opening in this silicon dioxide. And now by one of several mechanisms, we will introduce impurities into the silicon. The most common way these days is to strip electrons off of the atoms and accelerate them in a particle accelerator. That's an ion implanter. And we can put a bunch of impurities at a very thin layer, control depth below the surface. We can either leave the silicon dioxide or usually we'll grow some more at some point. And then we take the entire silicon wafer and we put it into an oven at high temperatures, and the impurities, dopant atoms, acceptors or donors or whatever, diffuse down into the surface. So the hotter it is and the longer we leave it, the deeper they will go. And so we have then impurities that have diffused to a predictable depth in a particular location. Usually there's silicon dioxide capping everything whenever anything happens because it's hard to avoid. So if this was, for example, acceptor dopants, then we would have p-type material into an n-type region. The n-type doping, as we come down from the surface, would be relatively small, and the p-type doping would be higher. It would be highest at the surface, that's where it came from, and it would have diffused down this gradient. Where the two are equal is the junction. And we repeat many, many times in many, many different places. All right? So that's the basic photolithographic process. And in this class, it's not real important that you understand it, but you can see that things have to go a little sideways. It has implications for the structure. The fact that these things are diffused from the top indicates that the layers are usually doped most heavily from the top, with some exceptions. Any questions? All right, different ways to form layers. Now, I'm going quickly through this because this isn't the main point. You can, when you grow the original crystal, you can include impurities and make it p-type or n-type from the get-go, from the time when you created the wafer in the first place. And so you can buy wafers with a particular doping level already built into them. All right? Another way is to have a layer and then deposit from the top. These are silicon wafers, however big, so mostly circular, carried in a boat of some sort that's just a whole bunch of wafers. And then we expose them to the stuff. If what you expose them to is, you can deposit different types of layers. You can deposit metal on top of something. You can deposit silicon dioxide. You can deposit silicon nitride. You can deposit silicon. If you deposit silicon on top of some other layer, then normally it will form into so-called polycrystalline silicon. Poly for short, but polycrystalline silicon has local crystal structure, but not long-range crystal structure. So there's grain boundaries in things. So mobilities of carriers are affected, and various other things are affected by it. Okay, so that's one of the ways, is to create polycrystalline silicon. Now the alternative, or one of the alternatives, is if you're very, very careful, you can take silicon, and if you get it clean and use the right conditions, you can actually grow the crystal structure up. Normal crystal is very pure and with a very regular crystal structure over long ranges. If you grow it just right, you can grow and continue the crystal structure up. And that's called epitaxial growth. And it's still used in a lot of processes, especially a lot of bipolar processes use this epitaxial or epi layer. Just epi. All right? Continuing the crystal structure. And the doping of this layer could be different than that one, so we could have p-n junctions in it. And that's used in a lot of bipolar processes. Another important way to form layers is by oxidation of silicon, which we already talked a little bit about. If you expose a silicon wafer to anything with oxygen in it, it's very reactive, and it will form silicon dioxide, so either water or oxygen molecules. Ways to put impurities into the material. The number one these days especially is ion implantation. As I mentioned, you just strip some, or just ionize whatever it is you're trying to put in there, and put an electric field on there and shoot the impurities directly at the wafer from above. How fast you shoot them, how much energy you give them controls how deep they're likely to go, and how many of them you do, the actual current integrated dose of that, you can count them. You can just integrate the current and figure out how much stuff you've put in per unit area of the wafer. So it's a very well controlled process. Question?
Can you also dope that and completely control it?
The question is, can you dope the polycrystalline silicon? Absolutely. So you could co-implant that with, you could put impurities in while you're doing it, or you could implant or otherwise dope it afterwards. And that's very commonly done, and we'll see a process that depends on that. So yes, most definitely polycrystalline silicon can be doped. Usually is. Okay, so ion implantation is the normal way. The alternative might be to first implant something, or otherwise you can deposit various impurities in liquid, crystal, or gaseous form, or you can have diffusion from one layer into the other. That's actually 4 different things. But ion implantation is the number one way, and diffusion after that. So a lot of times you'll implant or get a certain controlled dose at one place in the device and then diffuse it down. That's very common. So those are the tools that we have. There's, 5 minutes on all the processes that you can learn about and other things. So the main reason I want to talk about this is because it limits what kind of structures we can have in the devices. And when I say the type of structures, I mean from the top of the silicon going down and their shapes. A long, long time ago, they came up with this so-called standard buried collector transistor. Now that's an ancient process, and I don't think anybody still uses it, but maybe they do just because they still sell millions and millions of old devices, and so maybe they still use this process. I need to get somebody to answer that question. But it illustrates a lot of the key trade-offs, and so it's a good place to start. And it's also covered in the book. So to bake we're going to use an NPN structure, and the thing we're looking for, I'm going to erase this in a second, and please don't try and take notes following this, because I'm trying to talk real fast. I don't want you to be. So the structure that we usually want is concentric from the top down. Heavily doped N-type is going to form the emitter. When I say heavily doped, I put either N or P with a plus, and that means dope it as heavy as you can, 10 to the 19th or more. When it's doped very heavily, it acts just like a metal. It's very highly conductive. There's lots of electrons in this case, or lots of holes if it had been P+. Okay, so it's very conductive. Anyway, that's the emitter, and we'll make a contact to that. Then that is diffused down inside an existing layer, which is moderately doped p-type, which is the base. I need to tell you that it's very difficult to make a good quality non-rectifying junction between a semiconductor and a metal unless that semiconductor is extremely heavily doped. So we can make a metal to N+. To make a metal to P, we need a P+ region in here, and so there's our base contact. So it has to be heavily doped to avoid problems. We don't need to talk about the problems. Maybe we can later. Actually, we can exploit those problems sometimes. All of that is typically then done somehow into a region which is lightly doped, which is the N-type collector. And so this will be emitter, base, and then we will need a heavily doped contact somewhere. All right, so this would be the simplest emitter base collector, vertical NPN, NPN, and then the currents would have to go sideways. So this is the simplest thing you could imagine. It already has problems, okay? One of the things that I should say in general, I mentioned that when we have very heavy doping, N+ or P+, it's like a metal. There's lots of electrons or lots of holes. That means for any field, we don't have much resistance. If that makes sense, then you must understand that if I have relatively light doped region somewhere, if I have a lightly doped region somewhere and I put a contact over here and a contact over here, let's put P+ there and P+ there, this thing could actually be a resistor. The current would come down and make a good electrical connection here, but then this would be like lightly doped material. Because it's lightly doped, there's not many holes in that region, and therefore it's going to have a high value of resistance. Okay? It's going to have a high value of resistivity, which is per unit area or volume. If I make it thin, then it'll have an even higher resistance. If I make it thick, it'll have a lower resistance. So we have a thing called the sheet resistance, which takes into account, and I'll come back to this, but I just want you to have the concept that a thin layer with light doping is going to have a lot of resistance per unit length. So that's a trade-off. So if we have carriers that go from the emitter through the base and they get down into the collector, they're going to have to go through this. If this is lightly doped, then they've got a long way to go through highly resistive material to get where they're going. So one of the things we want to do is reduce the length of this path and have higher doping available. I'll show you what I mean in just a second. Are there any questions, though, about the concept of the relationship between the doping and the resistivity, and between the resistivity and the geometry, right? Longer distances with narrower layers means larger resistances. Yes?
Are N junctions rectified?
I'm sorry?
Are the junctions between the N+ and the N material? Do they do anything?
Is there a junction between the heavily doped and the moderately doped? It's a current can flow in either direction with no trouble. So there's a junction, but it's a high-low junction. It doesn't cause any buildup of charge. It's not a rectifier or anything. Okay, so it's not a junction in the usual sense. All right, so this is the structure we want. How do we get it? In the standard buried collector process, we have a so-called buried collector. We start with lightly doped N-type material, lightly doped P-type material, 10 to the 16th per cubic centimeter boron. All right, moderately doped, fairly light. We will, before we do anything else, where we know the transistors are going to be, we will put a so-called buried layer in. It's going to eventually end up growing above and below because there's going to be some stuff above. We put a lot of electrons around this region, and this forms a so-called buried layer. I'll explain why later, but that's an important part of the process. Now I'm going to grow the collector as an epitaxial layer. It's going to be N-type. It's an NPN, so it's got an N-type epitaxial collector, and it'll be lightly doped, all right? And this is going to form the collector. And we're going to grow it up to some depth, all right? This is going to be lightly doped compared with everything else we talk about, and I'll remind you why later. We're going to do an isolation, in this case diffusion, and it's going to go all the way around in at least 2 dimensions, and it's going to be really deep So I'm going to put N-type material, P-type material, heavily doped out to the sides. And this will go in 2 dimensions, will completely surround it. It'll be heavily doped. And this is going to be a connection. We'll make a wire connection to this down to the substrate. So this is our 4th terminal of our bipolar transistor is here. And it's got to come through this heavily doped region. And then this thing is going to go in 3 dimensions. It's going to come all the way around and surround this N-type collector on all sides with either nothing or P-type material. So there's a junction isolation all the way around. And we will make sure that this thing is always at the most negative potential in the circuit so that this junction never forward biases. All right. Now we can really start building the transistor. Somewhere in the middle here, vaguely, we will put a region of some depth that we control carefully, and it's going to be P-type. It's got to be more heavily doped than the collector was, and this is going to form the base. Somewhere later in the process, we're going to put in a P-type, a P+ contact to this, and there will be my base contact. All right? That'll have to be done probably later, and that should be fine. All right, now I'm going to make another masking operation, another photolithographic step, and I'm going to put in an emitter contact, and I'm going to diffuse it down so it almost reaches the base, and it'll be heavily doped N-type material. And then we've got to figure out where this is. We're going to make a contact to it, and this is going to be the emitter. The most heavily doped region is the emitter. It's doped more heavily than the base. Remember, we make the base, we put many more electrons in the emitter than we had holes in the base in order to get a high beta. Remember that from last time? Beta was mostly determined by the ratio of how many electrons we have versus how many holes we have. So we want light doping in the base to get high beta. Right away, you can see we have a problem. If this region is lightly doped and this is very thin, then what does that tell us? It's thin and lightly doped. What does that tell us about the... It's highly resistive. So that's a problem. We're going to have to model that resistance. So especially, we can't do much about this. There's a fundamental trade-off between the base width, the base doping, and how big it is. All right? And so this is a narrow base, and it's got some distance. There's going to be some distributed resistance there. So we wish we could get this in closer. We wish you had another contact. There's other things. We'd like to reduce the resistance in series with our base terminal. And we don't have many choices on that. Later on, I'll tell you about some that we do have. Remember that the width of the base is critical. We want all the electrons to go straight through. So the main thing that happens is, well, we're going to continue this. We're going to grow oxide layers, and then we'll actually carefully put all the metal layers where they are. And we'll have an emitter, base, and I forgot to put in, when I put in the emitter, I'll also put in a N+ region so that I can make a contact for the collector. All right? This is very lightly doped. So the emitter is heavily doped, the base is moderately doped, the collector is very lightly doped. We want the collector to be lightly doped. The biggest reason for making the collector lightly doped is that it means that the depletion layer between the base and the collector is fairly wide. This is the less heavily doped side of the junction, and we want to make this lightly doped. That makes it wide. When it's wide, that means it can support a lot of voltage before it reaches the breakdown field. So if we want large collector base breakdown voltage, this needs to be lightly doped. If it's lightly doped, then we've got a lot of a path. The main path in the transistor comes right through here. The electrons go like this, and now they start figuring out where to go. Some of them can go down here to this epi layer. Some of them may go directly this way. Some of them can go down through here, way over to here through a very conductive path and back up, and that's why we had the buried layer. And so we probably would have scooted this up closer. We don't want it too close. We want it just far enough so that the depletion layer will never bang into it. And then this buried layer reduces the total resistance of the main signal path, main current path here. So we have a trade-off between the breakdown voltage, which we'd like to be reasonably large, and the resistance that's in series with the collector. Yes?
So what is the reason for not taking the collector N+ region and just burning it all the way to the buried layer?
Why not take this all the way down? If you have a process where you can drive this in far enough, you will do it. But in early processes, it was just, there was like one depth. They wanted to do this and this at the same time, and that would have conflicted. As time has gone by, more and more steps, I mean, there's thousands of steps now. And these days, back in the 60s or 70s, this was like what was sent to the moon and stuff. These things, you know, every process, you know, double the price or something. So fewer steps was really important back a long time ago. Still adds to the price whenever you add a process step. So anyway, they'll eventually make contact holes and metal and a bunch of other stuff. All right, so that is the basic thing with a vertical NPN. Heaviest doping, moderate doping, light doping, trying to get our contact regions in as close as we can with as little resistance as possible. All right, a number of big problems here. The real problem is photolithography is still pretty good, but the ability to align two different masks, a mask to an existing layer, is not so easy. And so it would be nice if we didn't have to make sure this was fitted inside this region. You have to make everything big so that you don't accidentally miss. There are tricks that you can do called self-aligned processing that allow for better performance. Now, I'm giving you still something that's probably a 15-year-old process out of the textbook that is a variation on this one over on board 4. And this is on page 2 of the lecture 4B notes. So we go through a lot of this same stuff. We would start with a P-type substrate. We'll put in a big buried layer. We're going to use some more sophisticated processing. We'll have this N+ going everywhere. And I may have to draw a different picture of this. All right. If you put down so then we're going to draw an epitaxial layer. Epi, so this is similar to the other process. This is the N- epi collector. Now, 20 years later, these regions can be much smaller. They're probably more heavily doped. Heavier doping on the less heavily doped side means smaller regions. Smaller is better. Okay? As time goes by, the doping layers get higher. The depletion layers get narrower. Okay? But things are smaller. All right. If you put down silicon nitride on something and then expose it to oxygen, the oxygen will block the oxidation. The silicon nitride, I'm sorry, will block the oxidation. So you can get so-called localized oxidation. So what we're going to do, and you get this weird shape, but I can get a big old thick piece of field oxide, and the oxide is going to completely surround the transistor on all sides. So this is silicon dioxide, and this is going to be mostly an oxide isolated process. And it's going to work a lot better when we're all said and done. All right, so this is silicon dioxide. Silicon dioxide's an insulator, as I assume everybody knew. And I'm going to put in a big chunk of field oxide that goes all the way through the epi. So some more oxide into here. And that's going to isolate this contact over here. All right. Then I'm going to do the thing that somebody asked me about before, which is to put in a bunch of N+ over here, and it's going to be where my, so this is oxide, block all that out. Nothing's going, no carriers are going through there. Then I'm going to block out and put a so-called collector reach-through implant, which was the one you asked me about, and so I'm just going to put N+ way down to here, and now you can see I've got a heavily doped region. This is going to be my collector contact. It's going to come all the way over to here. Everything's going to be in close. So a little more complicated. And then we get to the good part, and I may have to blow this up a little bit so that you can see, but this is where the really good stuff happens. First, I'm going to implant a shallow base layer. So this is going to be P moderate doping. This is kind of in between P-type doping, and that's going to form our base. And the best part happens right now. I'm going to deposit polycrystalline silicon. I'm going to include heavy I think it's arsenic doping, so it's going to be N+. So I'm going to first put an N+ poly layer. I'm going to pattern it right over here somewhere. Let me see if I can get my geometry right. I'm going to pattern it, I don't know, somewhere in the middle. And then I'm going to remove the poly everywhere except for here. So this is N+ polycrystalline. It's going to form the emitter, but it's going to do it in a special way. Now the next part is the important part. I've patterned this to form the emitter, and now I'm going to do a P+ implant, a heavily doped P-type implant. self-aligned, so all this stuff, we are literally shooting these impurities at this thing in an ion implanter. Over here, they're going to be blocked by the field oxide. There's nowhere for them to go. Over here, they get right in, and they're going to form heavily doped p-type region that goes pretty much all the way through this, and it's self-aligned to this. Wherever the edge of this emitter is, this heavily doped contact is right next to it. And if I did this right, I guess this is going to go, I think I put this too far. It should have been patterned to be over here. So this is going to be p-type over here. Doesn't really matter over here. This will be fine. All right, so I think that's right. But the main thing is that it's self-aligned right here. So in many of the processes, as you see MOSFET stuff, you don't have to worry about two masks. This thing determines, the location of the N plus determines where the P plus base, heavily doped base part is. All right? Now, we get rid of all the masks. We do everything else. We take the whole thing and we put it into an oven. Some of the carriers, some of the arsenic atoms that were in this polysilicon that we put in here when we created it diffuse down. So they diffuse down, 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 and we get a silicon portion of this guy, and it's also N+. And it's self-aligned, and we stop that so that we have an extremely narrow base, it's lightly doped, and there's nothing we can do about that. So it's going to be resistive here, but by golly, there's a P+ contact right next to it. That's about as good as you can do. So this would be called a polysilicon emitter, self-aligned, oxide-isolated process. So not too bad. It's a reasonably sophisticated process. We'll do a few more steps. Polycrystalline silicon, you can use this as the emitter contact, or we can put some metal off to the side. We'll put metal here, metal here, metal here, and somewhere maybe in the third dimension, eventually we'll make a metal contact to the poly, and that'll be our transistor. And that now has this N+ as close as we can get it, the P+ as close as we can get it. The emitter is automatically aligned, so that's how I know the P+ is as close as we possibly could have had it. So the base resistance is as small as possible. That's probably as good as we can do. Why did the P+ not go into the poly in the first place? Oh, it will right up at the top. It'll form a little bit of a layer. That's all right. It's not going to hurt us. There's plenty of electrons. We can spread them out so it won't form a junction up here. That's always a good question if you're paying attention. All right, so that's a reasonably good way of doing things. Now, what does this whole thing look like from the top? I don't know if I left myself enough room. But each of these regions, let me just sort of draw them in 3D. And you can sort of see what would be going on here. So everything is like a perspective view. So this emitter might form a stripe. You'll hear emitter stripe. This whole region might completely surround it or something. I don't know, something like that. Then all of this stuff will be off to the side. This layer here is going to completely surround this thing with isolation in the third dimension and come off to the side somewhere. There's a contact over here. So if we look at it from the top, we're likely to see a N+ emitter. We're likely to see base stripes on either side, maybe going all the way around. So this is P+, but there's P- actually underneath this guy. And then, I got to erase some of this. I'm sorry. I didn't leave myself enough room again. But then completely surrounding all of that is isolation region. And somewhere in that is an N+ contact for the collector. So we'll put metal contacts here, and there needs to be room for contacts here somewhere as well. All right, and we'll run wires off for those. And somewhere not even shown is a connection to the substrate outside. The substrate's common to the entire chip. That's an important point. The overall substrate of the chip, remember it was whatever, P-type stuff. That's the whole chip. Physically, it holds everything together. Everything is in that substrate. Okay, so that's a typical design. Now, I must tell you, it's been years and years and years since I've had a student who did a transistor layout. Normally, this stuff, maybe all of this stuff, comes from the device design people, and they say, this is your transistor. If you want to make one that's twice the emitter area, then put two of them in parallel. or we'll give you one that's got a longer stripe. But in MOS technologies, a lot of times the students or the circuit designer does the design of the transistors themselves. From what I've seen, these days you just grab most of the transistors from a pre-designed library that some expert did for you. But all these trade-offs are worth knowing, and they've been on the quiz in the past. You know, what is the effect of changing the base doping? How does that affect various breakdown voltages and things? And we'll come back and say more about all those things before I would ask you on a quiz or anything. But that's the structure. These days, most of the technologies are optimized for building CMOS, complementary MOSFETs on there. There's some stuff in the notes about how that would go. So these processes where you just have NPN bipolar transistors, there's not very many of those at all. There are some really sophisticated processes designed for people like us that are designing good analog circuits where they have not only good vertical NPNs, but vertical PNP transistors. And we need to talk a little bit about that. And there are some very nice processes these days that use a few other tricks. Let's go back in one of these sort of standard processes and just understand what happens. Well, this has been optimized for this nice NPN device. As a circuit designer, we really, really want to have access to a complementary device. The NPNs are good. The electrons are faster than the holes. They have higher mobility. So we like NPNs for most of what we're doing. But we really like, because of the, as you'll see, it's really nice to have a good PNP transistor. Back in the day, when they first started this, they didn't have a way to build good PNPs. They were just glad they could get a PNP at all, right? We didn't want to add extra process steps. Using the same set of steps, I'm going to go to board 5, the most basic process is we can build a lateral PNP. And in the earliest processes, these were the only PNPs you could get. And this is described in the notes. And then we need to go back and think about our physics and see what kind of bad compromises we had to make to build a lateral PNP. So I'm looking now at page 7, 8. I don't have a picture of one. Yeah, I do. All right, best picture is on page 7 of the handout. So basically what we're going to do is we're going to take maybe this junction isolated thing with the P plus, with the buried layer down here, the N plus, the P, and here's the surface. We're isolated over here. And instead of putting in an N plus inside a P and then having a P plus region over here for our contact, that's what we had in the standard process. But what we're going to do to form a lateral PNP is we're going to take some of these P-type regions and put, say, 3 of them in here. I didn't draw it very well. But this is all going to be P-type, maybe heavily doped, I'm not sure. At any rate, the current flow is going to go sideways, laterally. Lateral means sideways. And this will then look like the emitter in the middle, and then we'll have base on either side. And then somewhere else here in the N-type epi, we'll need an N plus thing, and that's going to be the base. So these are collectors, and this whole region here is the base. So holes are injected from the middle one and just go sideways out to the collectors. So if we look at this from the top, starting in the middle, we would see, let me draw this a little more carefully. It'd probably make it like square or something. This is going to be my emitter, and then this little gap here, we're going to have to get through to get out here to this other P-type region, and the gap is made up of epitaxial material. So this is emitter in the middle, and the current will just flow sideways laterally out to the collector. And this is the emitter. And then the base contact would be a stripe over on the side. And this would be the base. Now, this looks okay the way I drew it, but these things have to be separated by a fairly large distance. In order to get good performance, we need typically a narrow base, and this thing doesn't necessarily give us a narrow base. This epitaxial region was optimized to make a good NPN. It doesn't necessarily make a good base. It's pretty lightly doped. So the base to collector junction, we've got all the breakdown voltage of this junction is not going to be very good. The breakdown voltage of this junction would be determined by the lightly doped region. and it's just not very favorable. So we get lousy betas. We haven't talked much about the speed of the transistor, but it's going to be lousy. These things are orders of magnitude worse than the corresponding NPNs. So a lot of early circuit designs, a lot of op-amps that you can still buy today still are based on the assumption that the PNPs are awful and the circuit designs are optimized. And we'll see that the circuit designs are optimized to take into account that the PNPs are just very poor quality. Question?
Go sideways, why not down?
Well, the question is, why do the electrons go sideways? These are holes, and they go because this is what the field is. So they're going to go vertically as well. So there's also a P in this way. So every lateral PNP has a parasitic, an unintentional vertical PNP as well. And if you really want to, you could have just used this PNP as a vertical device, and sometimes that's okay. So they don't necessarily know which way to go. The only thing they have is their diffusion and the electric field. And we wish that they would just diffuse to the nearest place where they can be collected. Yeah? The question is, why don't we make a symmetrical PNP? Again, that's what gets to be, well, remember that we started with things like the epitaxial layer, so we had to do some tricks to get the NPN to work. We can't just duplicate them again without starting from scratch with a new process. If we're going to choose one, we're going to use good NPNs and use NPNs as much as possible. So there's not an easy way to do that. Now, that was certainly true 30 years ago, 20 years ago. For the last 20 years or so, people have said, I'm willing to pay for it. I'm willing to do what it takes to build a process that is complementary vertical, NPN, and PNP. And the textbook, and we can go through it, but I'm not going to take the time, but the textbook explains some of the processes that are available to make good vertical PNPs. And that's called a complementary bipolar process. And they are available. Analog companies, I think Texas Instruments has a little of this. Analog Devices, still I'm pretty sure uses these. Companies that specialize in analog circuits may have these processes. The processes are 100 times or 10 times, I don't know exactly, more expensive than the simple processes they use for logic stuff. You know, most of the process design goes to building logic chips, microprocessors. And they use different processes. But if you're going to build a radio and you need good analog, or if you're going to build a strictly high-quality analog circuit, then it's probably worth having this in the process. There's lots of trade-offs, but they're economic ones usually. Okay? Other questions? Yes?
Start with a P substrate.
Why did we start with a P-type substrate? Again, we're optimizing for a good quality vertical NPN, and we wanted them isolated. So in all these processes, I erased this. Let's go over to the board 3 here. So I need the isolation. In order to be able to build multiple transistors in the same substrate, I need to have them electrically disconnected. And what I'm going to do, and now we can start some circuits, I'm going to put this at the most negative potential in the circuit, call it VEE. This is the positive, the P-type substrate. If this is the most negative DC voltage in the circuit, then there's no way to forward bias this junction. It's guaranteed all the time to be reverse biased. We hope. That's the plan. And so if this thing is at VEE everywhere, then that'll reverse bias it. And so we needed a P-type region for isolation. Now, if we had a process where we could build the entire thing on top of silicon dioxide and then do that oxide isolation on the side, we could get something that was completely oxide isolated. It is possible to do that, and some modern processes use so-called silicon on insulator technology. But it took them a long time to figure out how to do that, and it still involves compromises. But a lot of microprocessors use silicon on insulator these days, and so yeah, sure, no problem. If the microprocessor people want it, then we can all get it. Yes? Is it ever, do you do from both sides, top and bottom? There are some things that we do, but they're usually the people that build the micromechanical systems, MEMS and things like that. I don't think I've ever, I can think of very, very rarely occasions where people have tried to do things on the back. It's just not so easy to do. If we were doing this to scale, this is less than a micrometer, and the wafer's got to be 10 or 20, 100 microns, or else it'll break. So this is really, if this is a micron, this is an old transistor. A micrometer these days is a big, big area. 10 microns used to be a little bitty thing. Not anymore, right? Photolithography has moved so fast, so far. Moore's Law, all that good stuff. Okay, I'm sure there's lots of other things that need to be discussed in all of this, but I'm going to leave a lot of it for you to read so that I can move a little bit forward and start talking about how does the structure, all I have time to do today is introduce these concepts. How do these structures and the physical structure relate to the electrical behavior? And that is a question of modeling. Okay, so we want to have model parameters. Now, we already talked about some of them, and we already should have some idea what to expect about some of them based on what we've learned. So for every transistor, we're going to have a set of parameters. In practice, some intern or something probably had to go out in the lab. They came back from the fab. They cut a bunch of them up. They had test structures on there. They put them in packages, or they put them on the wafers and had this intern went out with a bunch of probes and a bunch of meters and things and made a bunch of measurements. They measured current voltage curves, responses versus frequency, and they extracted a bunch of parameters using some boring algorithm. All right? So if you go out to one of these companies, you could be stuck, getting these parameters. When you get it all done, a bunch of optimization happens, and you're going to give a list of 20 or 50 or 100 numbers, and the circuit designers are going to pretend that those are the truth for every device that's ever been made in that process. All right? So what do you have? You have the forward beta. You have the saturation current for the forward direction. Let's just see what some of the other things are. Those are the most important ones. The early voltage. Remember the early voltage told us about how the collector base voltage affected the current. It was a measure of that. The bigger this is, the less effect it has. So I have somewhere in the lecture, we're actually up to lecture 5. Maybe I shouldn't be. Maybe I'm too far down the road. No. So in lecture 5, I have a list of the SPICE parameters. And there's, I don't know, about 30 of them in the simple model. So there's a thing called IS. That's the saturation current. Remember, we used that one already. So somebody has to tell us what a typical value is. We have beta, and it's pretty much the value that we're going to use for beta. There's one in the forward direction. So almost all of these things have a forward direction and an upside down direction, right? So if somebody swaps the collector and the emitter, or if we go into saturation, then we're going to care about the reverse beta. I don't think they have, this becomes VA for forward. There's a VA for reverse. It's a symmetric device. I got IS here in 2 places. I knew something was wrong. Okay. Then there's a number of things that have to do with the details of the curves. We said that beta varies. We can get things off the Gummel plot. I don't want to list all of these, but this is a beginning set. And so we have a bunch of things that talk about that allow us to compute how beta varies as a function of bias, what happens at low currents and what happens at high currents. I guess I don't want to talk about that. We have things that tell us how much base resistance we have. That's modeled in series with the base terminal. And we've talked about why it happened, right? Because of the resistance between the active base underneath the emitter and making its way out to the contact. So a typical value of the base resistance might be 100 ohms. But if it's a really tiny device, it might be 500 ohms. So there's trade-offs. So different designs of transistors are going to give us trade-offs. There's a resistor in series with the collector. It's called RC. You take the transistor model and you just add internal to the model, you add this extra resistor, RC. Now notice that if the doping is very light or if the path is very long, then this RC will be fairly large. Typical value might be 100 ohms or so. If a lot of current flows through this, the external terminal might be at a fairly high voltage. This one might be at a lower voltage, and you'll get internally saturated. So sometimes that's called quasi-saturation. It doesn't look like it. This is the actual terminal that you see, but internally it's saturated. this voltage gets too low, this base emitter junction will forward bias. We'll begin to inject current the wrong way. We'll have a bunch of parameters for the capacitances. We really need to talk about those capacitances. They're really fundamental to the operation of the device. So maybe, let's see, how am I doing on time? Oh, I've got like 4 minutes. Let's use them. Let's talk about it. So capacitances are very important, and we haven't spent much time talking about them. So I'm on board 3 here. So we talked about distributed resistances here, 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 and here. So those are important. Let me clean this up and get back to the capacitances. Now, usually the most important capacitance in a transistor is the diffusion capacitance, and it's really related to, again, the variation of the base charge due to the actual current that is flowing through the device. So for reasonably high currents, we model this as IC over the thermal voltage times the parameter called tau sub f, and the SPICE parameter is TF. All the SPICE parameters have alphanumeric names. And that is, again, something that some grad student or somebody has to go out and measure. And it's in seconds, picoseconds probably, for a realistic value. And so that gives us the main capacitance, which is really the business end of the transistor. If you're going to vary the current that's flowing in the device, you have to vary the charge that's in the base. That's just fundamental. But in addition to that, there is a junction capacitance. And it's called CJE, and it follows the equations that we had. It's got an area factor that you can multiply by, and it's got a CJ0 divided by a 1 plus VBE. That's a forward bias, so I guess it's 1 plus, I guess it's minus, over some built-in potential. So there's a built-in potential, there's a factor here, a number for this, and there's a value for the built-in potential, and there's a CJE associated with the emitter, CJE0 or something. And the actual SPICE parameter is CJE. All right, it's really CJE0. And then that goes into our junction capacitance formula. This is the one that's usually forward biased, so usually you don't use this for hand calculations. We usually replace this by 2 times CJE0. Anyway, you've probably forgotten that, but anyway, that's what's going to happen there. This one is a pretty large capacitance per unit area because this is a fairly high doping. The high doping also means that it's got a fairly low breakdown voltage. The base emitter reverse bias breakdown voltage of a typical transistor is about 5 volts or less. That's actually pretty important. So you've got to be really careful if you accidentally reverse bias the base emitter junction, it can be damaged because of too much current flow or almost anything. So it's very sensitive. We really have to be worried about what goes on physically down in here. Then there are junction capacitances between the base and the collector. In the small signal model, we'll call that C mu, but in the SPICE model, it's called CJC, and it's actually CJC0. You get it multiplied by an area, and it's got a 1 plus minus whatever. The reverse bias from the collector base junction, whatever that was. There's a built-in potential. And this factor, this is uniformly doped, so this is usually 1/2, but it doesn't have to be. All right, so we have the same sort of model here. And there may be some other things that we can add. So this thing here is actually called MJC, SPICE parameter for that. And again, it's probably 1/2, typically, because this is uniformly doped. When the less heavily doped layer is uniformly doped, then you usually have 1/2 here. So there's a lot to remember, but you'll get it. There's also a capacitance from the substrate to the, so there's a collector to substrate capacitance, CCS. And it's a junction capacitance. It's got an area. It's got one of these kind of dependencies, etc. So there's a lot of repetition here. There's more details, but that's a pretty good bit, and that's probably about all we're going to have time for.